This recording is for Math 31, Module 6, Section 1. And the topic that we're covering tonight is maximum, or today, maximum and minimum problems. This is a bit of a throwback to Math 20-1. Now, I know Math 20-1 was a long time ago for some of you, but we approach these questions in Math 20-1 a little bit differently than we're going to solve them in this section. And you'll see that this is a lot more economical way to do it than the way we knew how to do it in Math 20-1. So I'll kind of relate the two things together so that you can see the crossover. So the first example that I've chosen is from your booklet. It's on page 5 and it's example number 2. And I'll just take a minute to write it out. So it says, find two positive numbers whose product is 108 and the sum of the first number plus 3 times the second number, second number is a minimum. So we start this question exactly the same as we did in 20-1. And as I say, I'll relate the two methods. Obviously, we're going to do the calculus method because we're talking about calculus here. When we're given questions like this, we really should have let statements. I'm not super picky about it, but really, if we're going to do a correct solution, we should say let x and y be the two numbers. Again, if you don't put that down, I'm not going to get too worried about it. It says two positive numbers whose product is 108. Okay, so x times y, product is multiplication, equals 108. And it might be worthwhile just to put these words down. Sum means add. Difference means subtract. Product means multiply. And quotient means you're dividing. I know that you likely know those, but just kind of rattling around. So we've got one expression. The product of the two numbers is 108. Then the second one says the sum of the first number plus 3 times the second number is a minimum. Doesn't actually tell us what the value is. So what we're going to do is we're going to make an expression, and instead of making it equal to a number, we're going to make it equal to a letter. Now, I like using the letter M for minimum. So this expression would be M equals, and then we just kind of have to start out figuring what the number, what the important parts are. The sum of the first number plus 3 times the second. Okay, so sum means add, first number 3 times the second number. So you do have to have a little ability to take words and get them into equations. What we're going to do now is we're going to try to get an equation with one variable on the right hand side. So like a quadratic equation is what we're trying to do. So it doesn't really matter which letter here, the x or the y that we solve for. It totally doesn't matter. I might as well do what they've done in your booklet here. So they take the x and they have 108 over y. Like I say, it doesn't really matter at all which way we go about doing this. And then what we do is we take this expression and we substitute it in for the x. So this again falls back to something that you would have learned in grade 10. Okay, so we get 108 over y plus 3y is the minimum. Now, what we had to do in 20-1 was we did something called completing the square. This is not quite a quadratic equation like we did there, but that was the process we did in 20-1. Here, what we're going to do is think about what we know about minimum. We know that minimum happens on a graph. If this was graphically done, I'm just going to draw a kind of graph. This is where a minimum happens. The slope at a minimum is equal to 0. Okay, and the graph goes from decreasing to increasing. So we know that slope is really a measure of the derivative. We're going to find the derivative, we're going to set it equal to 0, and we're going to solve. And that's the process. So M prime, I guess before I do that, I'm just going to write it like this: 108y to the minus 1 plus 3y, just so we have it easier to do. Okay, we drop the exponent down in front and we subtract 1, and then we drop the exponent down for the 3y, and we just get 3. Okay, now we got to solve this guy. So we relate this equal to 0 because we know we're finding a minimum, and we get minus 1 over 8. I'm going to put the y squared on the bottom, plus 3. Okay, so I think the best way to go about solving this is to move the 108 over y squared to the left-hand side. I change the sign, and then I multiply both sides by y squared. Okay, so then this cancels, and I get 108 equals 3y squared. And now that's a fairly easy quadratic, not even a factoring question to solve. We can divide both sides by 3. And we get y squared equals 108 divided by 3 is 36. And I'll just come up here, and we get y is equal to the square root of 36. So therefore, y is equal to 6. Now, notice that I didn't take the negative. We know that the square root should be plus or minus 6. But if we take a little quick boo back up at the question, it says we want to find 2 positive numbers. So that means that we don't actually need to include the negative part. The answer for y is just y is equal to 6. And then from there, we go back and we substitute it into one of the equations. The easiest one to substitute into is this guy. So we get x times y is equal to 108. So x times 6 is equal to 108. And so x is 108 divided by 6, and 108 divided by 6 gives us 18. So there's our 2 numbers. Okay, x is 18 and y is 6. Again, when we were doing this in 20-1, we would get down into here and we would complete the square if we had one. But for calculus, we are going to find the derivative, set it equal to 0, and solve. Okay, so we'll try another one here. We'll try a little bit more difficult one. Second one I kind of have queued up is from page 8. And I thought that example 3 was kind of a good one for us to go through. So I'll just take a minute to write it down. An open box is to be made from a square piece. Material. 30 centimeters on a side by cutting small equal squares out of each corner. Find the volume of the largest box you can make. Okay. Alrighty, so what we have, you might think way back to grade 10 when we did nets. And nets are something where you take a 2-dimensional object and you figure out how to fold it to make a 3-dimensional object. So here's our, oh, it's supposed to be kind of square. Let me draw a little bit better drawing than that. Okay, so each side is 30. What they're saying here is we're going to cut out a little piece here and a little piece here, a little piece here, a little piece here, and then we're going to turn it up, and that's going to be the height. Now we don't know how big that little piece is, so here's where we introduce our letter. And again, we should probably have a let statement. So let x equal the length or width, because it's a square of the cutout part. Okay. So what that gives rise to is the ability for us to find the new length, the new width, and the height. Remember, we're going to be turning it up. So this little distance here is going to be 30 take away 2x. That's our new width or length. Again, they're exactly the same numbers, but that's okay. And then this one over here, and highlighting it, this would be also 30 minus 2x. And then the height is going to be that piece that we cut out. So it's going to be this x. So let's just write that down. Length is 30 minus 2x. Width is 30 minus 2x. And the height is x. So it says we want to find the volume of the largest box you can make. Well, hopefully you remember our volumes formulas. And I think the formula sheet that I provide you is pretty generous. So I think that's probably on there. So the volume is the length times width times the height. So we substitute everything in. 20 minus 2x, 20 minus 2x, and then multiplied by x. And remember, this whole idea of maximizing volume, minimizing, etc. You're going to try to get an expression, take the derivative, set it equal to 0, and solve. Now, I think the easiest way to go through here is to get this all multiplied out. And I think I copied something wrong here because I see I've got a 20 there when I should have 30. We should do FOIL probably, then multiply through by the x, and then go from there. I think that personally would be the easiest math. So you can always pause the recording and do your math and then double check just so you get a little practice at your FOIL. I will do it here. You get 900, and then you get minus 60x plus 4x squared, all multiplied by x. And I'll just do it in several steps. So we get 900 minus 120x plus 4x squared, all multiplied by x. Now, I kind of like it in the order where my biggest is first. So I'm going to multiply through by x and then reorganize all at once. I'm pretty sure you guys can stick with me. Okay, so I multiplied this back through, and then I just put it in the order biggest to smallest. So not important, but sort of, I'm just so used to doing that when I'm doing my math statements. Okay, so that's our volume statement. And then again, we're going to take the derivative and set it equal to 0. So let's do the derivative first. This is pretty easy derivative work. 12x squared minus 240x plus 900. And we set v prime equal to 0. So we get 0 equals 12x squared minus 240x plus 900. Now, I'm pretty sure that we can divide by some common factor. Let's try. Oh, it's beautiful. Beautiful. We divide by 12. Lovely. Okay, so this becomes very nice. Minus 20x 900 divided by 12 is 75. And that's a pretty decent factoring question. Product is 75 minus 20 is your sum. So you mess around with your numbers. If you want to do a product sum chart again, feel free to pause the recording, check it out, and then come back to it. Otherwise, 5 and 15 are going to work. X minus 5, X minus 15. So we get X can equal to 5 or X is equal to 15. Okay, now let's just remember the parameters. I know it's kind of gone out of sight. We had a piece of cardboard, or well, material, they said, that was 30 by 30. There's no way we could cut little corners out, right? These were the X's of 15. So this is an extraneous root because it doesn't make any sense for the question. Now, the question originally had said to us, I'm just going to read it from the page here, find the volume. Oh, I'm trying to find the volume. Okay, so here's our volume statement. So we're going to put X in there. Double check. Okay, so put the 5 in there, and that should give us the largest volume that we can get. Do the calculation, and we should get 2,000 centimeters cubed. I suppose I should take a second to double check that that's what I get. So give me a second and I'll do that. Yep, bingo. All righty. Okay, so there's another example of how to go about those questions. Okay, the last one I'm going to do in this short recording is going to help you out with number 5 on your assignment. So just kind of tuck that in the back of your mind. Remember, right now, this is module 6, lesson 1 video that we're looking at. And this example comes from page 14, example 3. And it's got a little graphic that I'm going to upload here. Let's hope that it works out. So let's do that. Okay, came way down here, but that's okay. I'll just move it up. All righty. Beautiful. Okay, there's our little picture. And here's what it says. It says, find the volume of the largest circular cone can be inscribed in a sphere of 30 centimeters. Inscribed just kind of means inside, for the lack of tons of terms. Okay, so there's our picture. All right, we've got a sphere. It's a 3-dimensional thing that has a sphere of 30, radius. I missed the word radius. Of 30 centimeters. So it has 30 centimeter radius, and we're going to try to get this sphere in there. So it's kind of important that we draw on this diagram, try to kind of figure out what we're talking about here. Okay, find one of the ones that can be described in the sphere of. Okay, so if we kind of make a dot here in the middle. Okay, this would be our radius, and this would be our radius of our cone that we don't know, right? We don't know how big that radius is. We do know the radius of the sphere is 30. So let's see how we could draw this. If we had, and say somewhere arbitrarily, this is approximately the middle of our sphere, and we draw it down like that, that would be our 30. Okay, so you can see that we're sort of trying to massage a bit of Pythagoras into this, right? We've got a right angle. We've got R being our radius down here. I guess I should probably put in a right angle here. And then we're looking for some way of relating it. Now we've got a height here. So let's call, I think I'm going to change my pen color, this whole thing H. Okay, so the height of the cone is H, and so that would leave us with the statement for this guy here of 30 minus an H. Let me just bring it out here. Okay, sorry, h minus 30, wrote it the wrong way. Sorry about that, gang. Now we can write down a Pythagorean statement and then we can get going. So I didn't write any let statements. I think the H is self-explanatory, that it's the height of the cone and the R is the radius of the cone. And as long as we know some of our formulas, we should be okay to get going on that. Let's write our Pythagorean statement. So if we're looking at, I think I will just make it in green here, this nice green triangle here. We can write our Pythagorean statement to be 30 squared equals R squared plus H minus 30 squared. Okay, and we can do a little bit of reorganizing on that. Not terribly hard math. 900 equals R squared. This careful FOIL will get you every time. So we get H squared minus 60H plus 900. Let's do a little bit of reorganizing and kind of cleaning up. So the 900s will cancel here. And what we're trying to do here is just get some sort of relationship between R and H that's not too ugly. So let's move the H squared over to the other side and we'll get minus H squared plus 60H is one relationship to R squared. Okay, so now we've got something that relates to the R and the H. Now, volume of a cone. Again, if you're not sure of any of these formulas, just have a look and look them up. It's 1/3 pi R squared H. And you might be able to kind of pick up on the fact why we did the solving for R squared now, because we can just substitute directly into this. So this statement, I'll go back to a yellow highlighter, is now going to go in for this guy, which is going to make our life kind of easier anyway. 1/3 pi times minus H squared plus 60H times H. So we're going to mess that all around, make it look a little prettier, and then we're going to do the derivative. Okay, so I would multiply the H through, and then we'll multiply the 1/3 through. I don't want any brackets, so we'll get rid of the brackets first. So minus H cubed plus 60H squared, and then let's put the 1/3 pi through that as well. So 1/3 pi H cubed, we'll tuck the minus out the front, plus 20 pi H squared. All right, I think we're all good there. Okay, so now again, trying to maximize things, we take the derivative and we set it equal to 0. So we're doing the derivative of V with respect to H. I know that we usually just write that as V prime because our letters are not X and Y. I thought I would just remind you of how to do it with the D statements. And so we do the derivative. So we get minus 1/3 multiplied by the 3 pi H squared. So that was bringing the 3 down and subtracting. And then I'm showing all the work here. Okay. So then our derivative statement would be minus pi H squared plus 40 pi H. Okay. So there's our derivative statement. And then again, we set it equal to 0 and solve. So feel free to pause the recording if you wanted to and try your math on your own and then go back and check. Okay, so I'm just double checking that I haven't made anything, done anything too wrong. Okay, so let's equal it to 0 and solve. So minus pi H squared plus 40 pi H. We can get rid of the pi actually. And you know what I'm going to do? I'm going to divide by pi. 0 equals minus H squared plus 40H. And I don't like negatives, so I'm just going to move everything over to the other side. And then we're going to solve from there. So for here, we take out an H. We get H minus 40 equals 0. we get h equals 0, h equals 40. Remember, we're trying to find a height here. So again, we have an extraneous root or a non-permissible value. Doesn't matter to me what you call it, but we get our height to be 40. And I'm just going to quickly go back and read what we're asked to do. Find the volume of the largest circular cone that can be inscribed. Okay, so now we know the h value. So we have to go back and find the r value. So we need to take this statement, which was minus h squared plus 60h equals r squared. Let's put that down here. Okay, because we got to go back and find our r value. So we had minus h squared plus 60h equals r squared. Put our 40 in there. Again, I don't like my minus, my h being minus, but whatever. Okay, grab our calculator out and work that out. Let's see what we get there. So minus 40 squared is minus 1600. And then plus 2400. 2400 take away 1600 is 800. Again, when we're trying to find a radius, we have to have a positive number. So we're going to ignore the negative and kind of get an ugly number here. I guess we don't have to find the actual radius, but that's okay. I'm going to continue on my 28.28. So it's not a very nice number. Now, if you think about the volume formula, 1/3 pi r squared h, we really just need r squared. So we'll just kind of take it under advisement for the 28, because I'm so used to solving for just the actual term. So now we put everything in here. 1/3 pi, r squared was 800, the h was 40. Grab out your calculator one more time, do your calculation, and you should get, they rounded off to the nearest centimeter cube. Let's just see exactly what it comes out to be. It's probably not going to be too bad. Times 800 times 40. So 33510. So approximately 33510. And the units are centimeters cubed. Okay, so for these questions in this section, just to kind of wrap it up, normally you're going to find two equations to relate things together. One of them is going to be your statement that you're trying to maximize. You might have to do some substituting in, then you're going to find the derivative, set it equal to 0, and then solve from there. Depending on exactly how it shakes out, the solving is a little different question to question. Okay, I hope you found that helpful.